Okay, cool. I have everything set up. So, you had questions on how to do stuff with like the ALU or just
Yeah.
arithmetic circuits?
So I think my very first question is like how the homework is worded and like
Okay.
if I'm thinking about this right. So like number 2A.
Yeah.
So the first part we've like gone through how to actually make
The ALU.
sorry?
The ALU.
No, it's more like the components. Like, so for the first part, we had to draw the equality comparator and then do like less than greater than. So the second one is now working with the ALU.
Okay.
So expand the ALU, and we're just using like the standard one.
Yeah, the one that she gave you. Yeah.
Yeah.
And do you want to just add functionality to it, basically?
Right. So the first question is we're adding an XNOR and a NOR.
Yeah.
And I'm just wondering if like it just says expand the ALU to include the XNOR and NOR.
Yep.
Do I need to expand the mux at this point, or am I just literally adding the gates next to it and funneling the A and B through there?
Both.
Okay, so I do
So
need to
you want to be able to choose between those different operations. So you need a bigger multiplexer to choose between that many operations, right?
Okay, so that's what I thought. The only reason I was confused a little bit was because the next one was saying add an output to the ALU called V, and so I was like, okay, it didn't say output in the part A, so am I not?
It's just an extra one because the
Okay.
output here is result, and it's the same for all of them.
Okay.
Right. Even if you're selecting the ALU, the at addition, say,
Yeah.
the output isn't add, it's result. If you're anding all of them, the output is called result.
I understand. Okay. So then, am I overcomplicating it if I'm like, I was thinking for 2B or 2A, where are all my pages? So I was like, okay, I've got um, my XOR, or my NOR here and my XNOR here. And I'm thinking, okay, I already have an OR gate. Should I like branch off and do an inverter and then have this come out and like, well, I'll need to expand the bits, say like ALU control bit on the inversion part, and it's, or can I just like slap the gate right here, right there, and just put extra bits? Like, I think I'm overcomplicating it to start to.
You probably are. I
Okay.
think the last thing you said, the can I just do this? I think that was correct.
Okay.
So,
That's what I thought. I had to. So like, yeah, I had like drawn this whole thing, and I was like, let me invert this gate, so I'm not using an extra gate. And then I was like, okay, I'm gonna put a line out there for an ALU control of like.
So-
another bit.
so yeah, I mean, this is correct. This will work. Absolutely. The additional stuff, like you mentioned, is you have an extra inverter here, so you have the NOR, so you don't have to duplicate an extra N input OR gate. Awesome, you saved on that gate. And then you have your XNOR, and then yeah, you would absolutely need one extra bit for the ALU or for the multiplexer.
Okay, and then that's good. So that one was fine. How I was thinking about it. Okay, so I can just on my final page. Is good middle here?
Yes.
Okay, okay. Then I just have one more quick question, or I don't know if he wants to go through this one completely, because we went through it in class, but we didn't draw it, and it's like the drawing part is for part B.
Yeah. Let me. Did you have any particular questions, Gnu, or are you just coming in for office hours? Oh, actually, wait. Sorry, I can't hear you because I have my audio on the wrong thing. Give me 1 second. I always forget to do that. Okay, cool. Could you speak one more time?
Just here for office hours.
Okay, cool.
Thank you.
I always forget to do that. All right. So, yeah, we'll go ahead and talk about your question, which was about drawing the schematics for.
So then part B, we're doing the overflow,
Yes.
and we went through the logic in class. Like, I'm cool with the logic.
Okay.
And I know we need to add then another option for another bit for the box.
Uh huh.
I think I'm like, so this one I think is, it's different for if you're adding it, you have to like do an XNOR and an XOR, and then if you're subtracting it, you have to do 2 XORs. And I'm like, how is this all gonna fit? And then how am I going to choose the ALU bit that like chooses the gate?
Okay. So we care about one thing. So this is kind of like an external thing. It's not going through the multiplexer. This signal is something on the side.
Oh!
Right? It doesn't go through the multiplexer.
Oh,
It-
so I don't need to worry about that. Well, I need the ALU bit to pull it out of like the adder.
You're going to need some stuff from here, yeah, but
Yeah.
but this doesn't go into the multiplexer. It doesn't like possibly become result. This is a separate external
Separate.
like
Oh.
output. Yeah.
So even though it says it can't work when you're like if you're doing an and or
That just
XOR,
means that it should be 0 if you're not doing an add or a subtract. Because it's not possible to have overflow if you're anding two things or
Right.
oring two things.
Right.
That's all that means.
Okay.
So these signals over here are often called flags. There's, say, overflow or 0. There's the 0 flag saying that the result was 0. There's a bunch of other flags, but this conglomeration of flags that occur when you do operations in the ALU occurs. They get sent out as output signals separately from this.
Okay.
Yeah. So, like, if you're looking at a black box, no. So if you're looking at a black box, you have A, input B, a select line, and then you have result, and then here you have your flags, however many bits of flags you have. So it's a separate output. Okay, so we're concerned with figuring out, okay, what do we do? How do we detect overflow? So what is the general logic for detecting overflow?
Yeah, so we went through in class, for addition, the overflow is when you're like adding two of the same signs and your result is an opposite sign for your most significant bit. Which I made, my truth tables and I got my little logic there.
Nice equations, okay.
Okay. And so if this and this happen, then we have overflow. Or, oh wait, is it just, oh no, it's just this one then, right? No. Yes, I'm getting confused here too. I think it's both of them.
Let's go through it from scratch.
Okay.
Let's talk about it from scratch. It'll be easier. Okay, no, you're good. No worries.
I've been doing this and I'm just like,
It's very
I'm
easy to get
doubting
lost in
that-
the calculations and the truth tables.
Yeah.
Okay. So, just in general terms, if you're adding two numbers, so this is case 1. If you're adding two numbers versus case 2 where you're subtracting two numbers. So, if you're adding two numbers, what we say is, okay, if they're the same sign number, there's a possibility for overflow. It could happen. If they're opposite signs, it's just not possible. It can't happen. If they're the same sign, might happen. So if they're the same sign, maybe. If they're the same sign and the output is of different sign than one of your inputs, doesn't matter which. If it's of different sign, so we would do, I don't know what you would want to call that in short terms, but say out, same sign in, not. So here this term is saying the inputs are both the same sign. Here this term is saying the output is the same sign as the inputs, but then you negate it, so it's not the same sign. So this means that there was overflow in the plus case. In the minus case, it's kind of the opposite, because when we're taking a number A and we're subtracting a number B, that's the same thing as saying A plus negative B. So in this case, we say, okay, when can we have overflow? Well, thinking about it like this, we say, well, if A and B are the same sign, then we're just subtracting two numbers, in which case it's not possible to get overflow. So actually, in this case, if they're not the same sign, then there's a possibility, because there's two cases. If A is negative, then this is going to be a negative plus another negative. Or sorry, I forgot to say, if A is negative and B is positive, then that happens. So that would be if A is negative, B is positive. This happens. Okay, but in the other case where they're flipped, so A is positive and B is negative, well then the negatives cancel out. So they're the same sign in this case and the same sign in that other case. So in general, if they're opposite signs, when you're subtracting, it's basically the same as what we were saying before, same sign for addition. Because of this minus sign, it just flips it. So all of that out of the way, we know that the minus term is basically the opposite of the initial term. So if this one said they're the same sign, here we say not the same sign. And then here, if they're not the same sign, and, just like the last one, and if the output is different sign. So if the output sign is different than the input. So again, this is saying if the two signs are different, and then we have to be very careful here, which input, because here it doesn't matter, I can pick whichever one. Here though, which input do I compare? I look at the A input. Yeah. So I would compare the output to the A input, and I say, okay, well, were they different? Yes or no? So this signal here, same sign, is dependent on the bits of A and B. So they're the same sign. So let's do the most significant bits. So I'll say this is a 32-bit ALU. It doesn't actually matter. Here you would say n-1, bit n-1, the topmost bit. And so what you would do is say, okay, well, my topmost bit represents my sign. If the signs are the same, then my XNOR gate output's true. If my signs are different, then my XNOR gate output's false. Now, I can also, just so that I have both signals available, I'm going to do it like this. So this is saying they're the same sign, because it's just XNOR.
Mm-hmm.
And this is saying they're not the same sign, the opposite.
If it's the same sign,
And we need that because we want one for same sign, one for an opposite sign. That's why I'm doing it like this.
I thought it was the same. If it was the same sign, it's XNOR.
Same sign is XNOR, yeah.
Oh, it is X.
XNOR, or XOR, and then you invert it, that same sign.
Oh, that is an XOR. Okay.
Yep.
Yes.
Yep, that is.
Okay.
All right, so here I have these two signals, and now I have this part done, so I'm good on this.
Oh, so we reuse. We can reuse.
Yep.
Okay. Yes, this is exactly what I'm like getting bogged down on. Okay. Yes.
Now we have to check if the output is the same sign as the input A. So we're going to compare it to A. So we say, okay, we're going to have to compare A with result bit 31, or bit n-1. So let me just write that in. So we leave it in general terms because that's what you'd have to answer on the homework, n-1. Okay. Now, we do exactly the same process, except here we only need one of the signals. We don't need both. So I'm not going to draw it like this. I'll draw it just as the XNOR gate. And actually, we want to know if they're not the same sign. That's what we care about, right?
So yes, that one has to be opposite sign.
So I'm just going to do XOR here,
Yes.
because that'll
okay.
determine opposite. So I say, okay, I'm going to take A bit n-1, and I'm going to take the n-1 bit of my result, XOR them, and this tells me if my output is the same sign as my input. I forgot the bar. If they're not the same
that's
sign.
The opposite sign.
Yes,
of our
yes.
Input. Yes. Okay.
Okay, so all the hardware that I've used here, this is a single bit, these are single bit values, these are single bit values. So I just have a 2-input XOR gate, another 2-input XOR gate, and an inverter. And all I need to do with these signals is take either of these, and I say, well, the overflow happens if this happens, or if that happens. But I haven't fully written out the equations. I've left part of them as an abstract detail, this part here. This happens if we're adding. How do you know if you're adding?
We use we know we're adding because we've got our ALU control second bit, the first bit, last bit is on the summer.
So the least significant bit
Least significant bit's the other
determines
ones.
whether or not you're adding or subtracting.
Right, and then this one means we're subtracting. Least significant bit equals 1, we're subtracting.
Yeah. So here's what I'll do. So for the subtraction case, when the least significant bit of the multiplexer is 1, that corresponds to the negative case, right? So what I'm going to do here is I'm going to say and then I'm going to put what is it? ALU control?
ALU control.
Okay, that's a lot. I'm going to say ALU C bit 0.
0. And then can we do ALU C 0 bar?
Yeah.
Just not.
Yep. ALU C 0 bar.
Okay. So I see. Yeah, I way overcomplicated this. I had like opposite sign instead of just like the same sign and then a subtraction.
Okay, so we're in agreement that if the first thing happens or if the second thing happens, we get overflow. Okay, so I can combine these two equations. I can like write it out on one big line. There's a few simplifications I can do. You'll notice that out same sign as in is out same sign as in bar is present in both these terms, so you can actually factor it out. And then you'll also notice that ALU control, these leftover terms, are the XOR of the two,
Okay.
right? Because if you have A bar B or A B bar, that's what I have here with these two guys. That's your A, that's your B. And so what you can write at the end is the overflow occurs, V occurs if, and then I'm going to write down what I had. So I factored out bar SN. So I factored that out, and that's factored with an and, so I put that and there. And then it's the XOR of these two guys. So I have same sign XORed with the bottommost bit of the ALU control. That's the overflow.
I would have never come up with that. What if you come up with like 8 million gates?
It'll work though. If you come up with those 8 million gates and the equations work, it'll work. There's nothing wrong with it. It's a stepping stone to get to more optimized stuff. But again, I mean, as long as you get the process, that's the most important part.
Yeah, like I think I would have like put those two together on the bottom.
Mm-hmm.
And, gosh, this is so confusing. Okay, this
Now-
makes sense. I just like.
All right, we're almost done.
Yeah.
There's one last little bit, which was what I hinted at earlier, which is that we're only doing this should only be on if we're actually doing an ALU operation. Now, our ALU operations occur when the two other bits of my ALU control select line are both zeros. That's the only time this should ever be on. So in other words, I would say and ALU control bit 1 is off and ALU control bit 2 is off.
So.
So,
Um,
so just for this part here, that's
Yeah.
saying there was overflow. But
I can only do it when you're using this.
yeah, what if you were anding two things?
Yeah.
Yeah.
Well, if you're.
So if you were
yeah.
anding two things, overflow should be 0. Even though, say the two numbers you anded, if you had added or subtracted them, yeah, they would have overflowed. But the operation you did wasn't adding or subtracting; it was anding. So overflow should be 0.
Okay. Yeah, and the only time
That's
you
what this
use
is
the
taking care of.
and is when you have no.
Well, and
C1s.
occurs when
Sorry,
C1 is
yeah.
on.
Yeah.
So this would force this to be 1 negated, which is 0.
Yeah.
And then 0 anded with this mess is going to force it to be 0. Or in other
Okay.
words, I mean, another way of thinking of it is these only happen if the top two bits are off.
Or 0.
So
yeah.
that bit is off and the topmost bit is off.
Okay.
Victor,
Yes.
we can choose this, right? Like, it doesn't always have to be at the least significant bit. We can choose
yeah,
to
you
be.
can swap them around.
Yeah.
Yeah.
Okay.
Yes. You You can order the multiplexer terms however you want. The only thing I'll say is that depending on how you order them, you may or may not have an extra gate or two, just because you lost out on some optimization. For example, like this one, if these two terms didn't have both the same top bits, maybe this one said 0, 1, 0, so you swap those two, then the logic here would be different. And so you might involve an XOR gate instead of an AND gate, and it's more hardware. But the general idea is the same, yeah. So you can choose the bits however you want.
So now we do like a V, and we need an ALU control line coming
Yeah.
into.
So this was already part of your,
Yeah.
I need to erase some of this mess. Boy. Okay. So yeah, those are your 3 ALU control bits. Right? And we'll also say, oh, okay, well, this also has to send those bits over to the overflow calculation mess.
Okay, so just
So I would probably do it under just so you don't run over all the other mess. It doesn't really matter though. But yeah, so you need that signal over there, and you say, okay, how do I make this? I'll do it over with this stuff because this is where I've drawn my gates already. But I have the signal for SS. I actually don't need SS bar because of that simplification I made earlier. I don't need SS bar, so
Yeah.
I don't have to use this signal. But I mean, I can still leave it. It doesn't hurt. It doesn't cost me any extra hardware to have this wire running. So I'll leave it for the moment. So I need this guy. I need this one. I need ALU control bit 0, 1, and 2. So all of them. So here's what I'm going to do. I'm going to XOR ALU control bit 0 and SS. So I'm going to take this wire from SS. I'm going to say I'm going to XOR that with. This is 1 bit. This is ALU control bit 0. Ow. So I'm going to take these two and I'm going to XOR them. So that's for this part here. And then I'm going to take that value and AND it with 3 things. The things I'm going to be ANDing are the other ALU control bits negated, in addition to this signal negated. So I'm going to take the other 2 bits here, and I'm going to split them off. So this is ALU control bit 2, ALU control bit 1, and then I have this signal here, which is out SN bar. So now you take all these guys, and I say, I'm going to AND them together, and I'm done. Let's see. Oh, I need to put inverters here. That signal, and invert this signal. That signal does not get inverted because it already is. And I believe that's it. So it looks like we used 1, 2, 3 XOR gates, an inverter, not an inverter, 3 inverters, and a 4 input AND gate. And that hardware is all going to go over there. I just have drawn it to the side. Yes. Okay. So now that we've talked about that, do you have any other questions?
So subtraction, we have
Oh, and I forgot to put the this guy. 1, 0.
yes. Okay, so we have the opposite at the same sign bar, which is, yeah, so I think this makes sense. I'm
Explain
gonna
it to me.
redo it.
Explain it to me right now, and that'll help you understand it better.
Yeah, so I think I was getting tripped up because on my subtraction, so everything with the addition, I had the way you did. On my subtraction, I had, like this was opposite sign. So I had opposite sign, and I actually came up with 2 XOR gates. With
I mean, opposite sign means the same thing as not same sign.
yeah, so that I had XOR'd with the added 2 XOR gates. Oh, but you do have 2 XOR gates.
One to make the same sign business, and one to make the
Yeah.
if the output and input are the same sign.
Why do I have an XNOR? Oh.
Well, I have an XNOR gate as well, right here.
Oh, okay. Yeah, I think it's. Okay, so in my schematic thinking, I was going to have an XNOR, an XOR, 2 XORs, 1 XNOR, like separate from an inversion of the XOR,
Yep.
making it an XNOR, which was like blowing up into this huge crazy thing. But
Mhm.
I guess it would still work that way. You just make it very nice looking. Okay. Okay.
So there's many ways to go about this.
Yeah.
I mean, this isn't the only correct way to do it, nor is it necessarily the most optimal way to do it. There probably is some other way to do it more optimally if you swap around some numbers for the multiplexer and do some other mess, but that's not too much the point of this. The point of this is to understand how to add functionality to your ALU. So if you want to design a processor and you're asked to also make it so that you can multiply 2 numbers, well, now you have to make a multiplier circuit off to the side and then run it through the multiplexer and say, okay, I need to be able to select the multiplier circuit when this happens, but I need to also be able to detect if my multiplications overflow the number of bits or that kind of mess. And there's just a whole other stuff.
Yeah, okay. Okay.
Cool.
I think this is good. Yeah.
Okay.
It's kind of sinking in a little bit.
Good.
I think I actually did do.
Okay. Did you have any questions for me, Good Noodle?
I was just thinking about what you said about like some optimization can be lost when we're thinking about the ALU control and some muxes. So is there like a general like way of thinking about it, or is it just trial and error?
So here's what I'll say. You can like go about it like mathematically rigorously to prove that there is some optimal. Don't do that. You can absolutely, and some textbooks go into a little bit of that stuff, but it's not really something you should be concerned about because most of that optimization can be handled by a synthesis tool. When you design your Verilog logic, it'll take the gates and optimize them pretty well for you. So absolutely, there's some level of optimization to be thought of, but at that level, I wouldn't bother.
I see. Thank you.
If it's plainly obvious to you and it's easy to do, go for it. Otherwise, don't think about it too hard.
Was this confusing to you when you first started doing it?
Oh my god, everything was so
Okay,
bad.
good.
It was awful.
I think like just seeing that you understand it now and that like it will come makes me feel a little bit better because right now this is very confusing.
Yes. I was very confused all the time.
Okay.
I did fine in the class, but I was pretty confused most of the time. I had to review the slides quite often and stuff like that. Any other questions for me? Either in regards to this or something else? Okay. I'm going to go ahead and erase this then.
Oh, can I ask a really quick question?
Go for it.
Just whether like my syntax or like my schematic is okay.
Sure.
So when we're doing like when we're doing a summer and let's say it's separate because the first part was just separate of the ALU controls.
Yep.
So I just wanted to show how I'm if this is B minus A, so this is my summer, but I'm inverting it, but I wanted to add the 1
Yeah.
to make it a 2's comp. Can I just stick a 1 up on this little second side of it? To like show I'm inverting it, adding 1, and then I'm pumping it in to like
Yeah,
full
yeah,
sum?
that'll work.
Okay, so
Um,
that looks okay.
So this is just if you want to make a subtractor, right?
Yes.
Yeah,
yes.
if you're just trying to
This
make a
is my
subtractor.
subtractor made from 2 adders.
Yeah, you could do it with just one though. So there it is. So what's the difference between a full adder and a half adder? Do you remember?
Um,
So a full adder has a carry-in, whereas a half adder does not.
oh.
So they have a carry-in. And this ALU, or this adder, is a full adder, therefore it has a carry-in, right? So you can carry in a 1
Oh.
if you're trying to make this a subtractor. So you fix that to 1, if this is just supposed to be a subtractor. And you say, okay, yeah, I'm going to invert all my bits of A. Though typically, I guess it doesn't matter. And this would be your subtractor. Let's think about what this does. We originally, if this was 0 and that wasn't inverted, do A plus B, and we get A plus B here. Let's think about what it does now. We're doing A added with the negation of B, but we're also carrying in a 1. So in other words, this is like saying B plus the negation of A added with 1. And remember, this by definition will make it a negative.
Okay. Yeah, for some reason I was thinking I had to do this first.
You can, yeah.
But I don't have to because it's cumulative versus you can just do it all together.
Yes. Addition is
C.
commutative. Doesn't matter the order. I have a way for remembering it, but I can't say it on on video. Actually, no, I can. Associative, I think of the A for annoying because associative was the one with 3 terms. That's more annoying.
Oh, okay.
Commutative is the one with 2 terms, so it's easier. You swap the 2 terms. Associative is the one with the parentheses that you move.
Oh, yeah. Okay. I will totally remember that. Yeah, that seems a lot easier then. Am I gonna get docked for doing it two sums?
I mean, if you you probably will, but not that much. It works, but it's not like the most optimal thing.
Think so. Okay. Thank you.
Yep.
So this is a full adder.
Though it is important to note what the difference is between mine and yours. So they functionally do the same thing, but here I have a single adder. But how many bits is this adder?
How many bits is that? That's
N bits, whatever you want to call it. Say it was 32 bits. Most of the time, though, now we have 64-bit registers in our computers, but I'll go 32. Okay, so we have 32 bits. But what you had up before was another 32-bit adder.
Oh,
That's a lot of hardware.
yeah.
So
I
you
see.
doubled the amount of hardware by adding in that extra adder at the front.
This is much easier. And then I don't have like an extra internal signal that's like some that's then feeding into the other signal.
No, should probably put that one back. Any other questions for me? It's fine if you don't.
Oh,
What's up?
so you said that you're an intern at Altec, right?
Yeah, I just got hired. They emailed me a few days ago.
Oh,
I'm going to be
congrats.
starting on the 16th. Thank you.
Congrats. How was their process? How was it like being an intern?
You mean like in the interview?
Uh, or like, what were you actually doing once you got the
Well, that's
once
the
you
thing.
got that role?
I just got told that I have received the job, but I haven't started yet because I start on the 16th.
Oh, okay.
We still have to review the end of the question.
That's what I was going to say.
Yeah.
I was going to say if you guys want, we can talk about the interview question that I gave you guys.
So good noodle on it.
Yep.
Anybody else?
Nope.
I think that would be cool.
I'll let you find your stuff. Good Noodle, did you think about the interview question that I gave you guys? I can't remember. Last week sometime.
Yeah.
Yeah.
So, firstly, how long did you guys think about it? I don't expect you to have thought about it for more than like an hour. At
Yeah,
most.
it was. I thought about it for a little bit, like less than that, like maybe 30 minutes.
Good.
Because I was like trying to work out the homework. But yeah, can we like look at the like state transition table first? Or I don't like. I also am still caught up on like one hot encoding for this.
Yeah,
which
don't.
is-
So, for this problem, the main thing is making the diagram. Don't worry about
Yeah.
actually making the schematic. Just the transition diagram. That's all we really care about.
Okay.
Because that's like the most important part of the design process. Once you have that, literally, there are some tools that let you put in that diagram as that diagram onto the software, and it creates the schematics and stuff for you.
Oh, that's cool. Interesting.
Yeah. I think you can do that in Quartus. I don't remember. I'm pretty sure you can.
Is Quartus, for what we've been doing in the lab, spits out the transition table based on the logic, but not
You can. I'm pretty sure you can give it a diagram. Well, it doesn't matter, but I'm pretty sure you can, and other ones too. Anyways, the most creative and like important part of the design process is making the design table, the diagram. So let's talk about it just as a review. The point of this FSM was to make a keycard detecting circuit on a door, which, generally speaking, opens or closes if the correct thing has been swiped. If the correct thing is not swiped, nothing happens until you do 3 incorrectly in a row, in which case an alarm sounds, locks the door, and then you have to swipe it correctly with the correct one in order to get what's it called? In order to get the alarm to shut off, and then the door still remains closed. So, like in every FSM, what's my first state going to be?
your reset state.
Yeah, I'll call it the reset state.
Yeah.
Okay. I mentioned in passing before that if you get all zeros, then that means that there was no key card. So I'm not going to draw it, but on every single one of these transitions, if you get 0, 0, you stay in the same state. Nothing happens because no key card has been swiped. So it's just like here. See how I only draw a single reset? Well, that reset actually comes from every bubble, but I'm not going to draw an arrow from every bubble if I know what this means. Because yeah.
Oh, sorry, I didn't mean
No,
to
you're good.
interrupt.
You're good.
No, I thought when we had the 0, 0, 0, we would go back into reset for the transition table.
Nope. This
Stay
corresponds to
in our-
no key card, which is to say, we didn't swipe anything basically. So should the state of the door have changed? No, because nothing has changed at the input. So like I mentioned, at every single state, you would theoretically draw a circle or an arrow to itself, which only occurs if you get all zeros. I'm just going to say verbally that that's what's going to happen because I don't want to have to draw that for all of them. So if we get all zeros, 4 bits of binary 0, then that means stay in your current state. Whatever your state is, remain in it. All right. So now let's pretend we have just gotten, let's say in the reset state, should the door start locked or unlocked? I think locked is pretty reasonable for the reset state, yeah. So let's just assume then in here we're locked. So I can write that as an output. But like I mentioned last time, there were two outputs we had. There was alarm and there was light. But the light corresponds to whether or not the door is open or closed. So I'm actually just going to use light here. So in this state, in the reset state, the alarm had better be off, and the light had better be off as well, because that means that the door's closed. Now again, I'd have an arrow from here to itself if we get all zeros, because nothing's changing. If we get the correct key card, which I told you guys was this binary sequence, or 6, if we get the correct key card, so I'll do 6 there, what would I do?
So you go into your light state. Or your output is light, but what it, like, I don't know, I just named it state 0, 1, 1, 0.
Let's call it state open. Doors
Okay.
open.
Can I ask a quick question?
Yep.
How come we didn't? So we have output for alarm.
Yep.
Output for light.
Yep.
Why aren't we doing anything with locked?
Excellent question. That's an excellent question. So, if the light is off, what does that mean the door is?
It's locked.
It's closed. If the light is on, what does that mean the door is?
It's open.
So by definition, it's just the
Light
the
0
negation
is
of this.
locked.
Yeah. So you totally could make a separate output signal, but that wouldn't really correspond to stuff in your FSM. All you would do is you'd have your FSM here, and you have two outputs of it. You have alarm, and then you have light. And you would take off one of the bits of light, invert it. That tells you whether or not your door is open or closed. So that tells you your door state, and you'd send that over to your door lock. So this inverter doesn't need to be in the FSM, so I'm not going to think about it too hard. But that's why. That's why I don't have it listed as one of the outputs. Yep. All right.
Okay, so you didn't. Okay, you named your state SO. But then later, like, we're gonna encode it with the line. Okay.
Yeah, I'm just naming it stuff
Okay.
that makes sense to me. Okay, so let's pretend we were in the reset state, and we had a keycard swipe. There was a keycard swipe, but it wasn't 6. What should we do with that?
Okay, so I was thinking there'd be like a state for each time you failed.
Okay,
So like this would be like S, like
F1, state
yeah,
failed 1.
like because we need to get to 3 and then the alarm opens. But like nothing is. It's we're just gonna have it locked. So it would be alarm equals 0, light equals 0, but like also would be like S closed 1 or like.
So I'll do
failed
that. S closed 1, which is to say that the door is currently closed, and we failed one keycard swipe, but we haven't like done any alarm mess or anything. Okay, cool. So we have alarm equals 0, light equals 0. Okay. Now, that seems to be every case from SR. We had the case where if you have 6 or it's not 6, and we also have the case for if it's 0, you go back to itself. So I'll just put that for this guy, but I won't draw it in for the rest. This arrow is going to be present on all of them. All right. So now the next thing I'm going to ask is, well, which path do we want to go down? Doesn't matter to me. We're going to have to do both anyways.
We can continue with the failure one.
Sure, yeah. Okay, so what should one of the transitions be, and where should it lead?
6 bar again.
Okay, so 6 bar again, and where should that go?
To like SC2.
Yeah, sure. So we have 6 bar again, so we get a wrong input again. It's not 6. So we say, okay, we're going to say this is my second closed state, i.e., I failed it twice, but it's still closed, no alarm has gone off yet.
Or stay close 1, wouldn't we be able to input a 6 and that would go to state open, right?
Exactly, yep. So that's my other case. If I get the correct input here, well, I'm going to ignore this path that I was going down and I say, okay, well, actually, that was the correct key card. So let me go ahead and open the door. So I go to S open. Exactly, that's right. What do I do now?
Gosh, this-
You want to go this way still? Okay, yeah.
let's just finish that.
So let's say we get S6 bar again, or 6 bar again. We don't get 6. What do you want to call this state?
You can say it's like SC3 or like
Yeah, I'll call it SA for alarm
SA?
state.
Okay.
Yeah. You don't have to call it SA. It just makes sense to me, so that's all right. So in this state, my alarm is going to go to 0. Or sorry, it's going to go to 1 because my alarm's on. And my light is still going to be off because my door is closed. Okay. And what can we do now?
So we can also, I mean, every single one of these with a 6 is going to go to open, but did we say if, I thought we said if the alarm is going off and we correct swipe it, it's not going to open the door, right?
Correct. Yes. So this line
So
is
that
actually
one
wrong.
is not right.
What would I do with this? Where would I put it?
I think, does it reset? Like, do we have 3 extra times now to fail again?
Yeah, that's right. And I go to this state. These two are kind of equivalent in a sense. So this is the neutral but open. This is the neutral but closed door state.
So you, in theory, if you set off the alarm, you'd have to swipe it twice in a row for it to open.
Correct. What happens if we're in the alarm state and we don't get 6?
We just stay in our alarm state.
Yeah, the door's closed, the alarm's blaring, you're like, come on, open,
Yeah.
open. It's still not going to open for you. It's going to stay in the alarm state. So we say, okay, no matter what I do, if I don't put in the correct key card, I'm going to stay in the alarm state. So I've actually finished up this guy. I've considered all the cases. Finished up this guy. I've considered all the cases. Considered all the cases here. All the cases there. So let's start on this path. What would I do first?
Didn't you say that if the light's open, you would need the correct key card to close that light, right?
If the door's open
Okay.
and you swipe the incorrect key card, it'll still stay open, but well, yeah, it'll still stay open. That's right.
Okay.
The but I was adding there was if you do it 3 times incorrectly again, even if it's open, it's gonna lock and then alarm.
Oh.
Okay.
So if it's open and it's not 6, you need to go back to SC1, right?
But is the door open here or closed?
It's closed.
But what do we want it to be? If it's already open and we swipe it and it's wrong, it's still
Oh.
gonna stay open, right?
Yes. Wait. Yes, until you hit 3 times.
So actually, it's almost this state.
Yeah.
It's the
but
same
on the
idea,
other side.
but it's separate. Yeah, a separate branch. All right. I'll call it SO1 for open. So I'm going to
Our light
say,
is still on here.
yeah, our light is still going to be on. So actually, let me write that in here. Alarm is equal to 0. We're not alarming, but our light is actually on here because our door is open. So we go this way if we get the incorrect input. But actually, what happens if you're in this state and you do the correct input? If you swipe it and it's open currently.
I think we should go back to SR.
To SR, like this?
Yes, because we haven't done anything incorrect yet, so we wouldn't be in SC1.
But we want to close the door.
Close the door.
So yeah, SR. And maybe I'll even rename this. It is our reset state still, but I'm just going to name it S closed. To kind of show off the relationship between these two. Very similar. And I'll erase this. Okay. So we just finished all these guys, and we've just finished this one for the case where it is 6 and it's not 6. Let's start with this guy. What do we do now?
SO2, if it's not a 6.
If it's wrong,
Yes.
we go SO2, yeah. I'm not going to draw it that way. My head's cutting it off. Okay, let's do it down. And actually, inside this state, what should I put for my outputs? For alarm and for light? In both of these. What do you think, Good Noodle? What should I put?
Shouldn't the light still be on, and then the alarm should be off?
Exactly, yep. The light's still on, i.e. the door is still open for both of them, but the alarm has not triggered yet. Okay, let's see. If we're in these guys and we get a 6, where should we go? So if we get the correct keycard swing, and we're in either of those states. What do you think, Good Noodle?
It should just be like state open, right? In which it goes to state reset or state closed now.
Correct. So currently our door's open, but when we swipe it and the door's open, we want to close it. So yeah, these guys are both going to go back to S closed. Okay, cool. So we've handled all the cases for almost all of these. Just SO2 is the one we have left. What happens if we get the incorrect input? 6 bar. Where would we go? Alarm starts going off, yep.
Incorrect. Oh yeah, so we have to go to SA.
Exactly. You wouldn't have a separate state here because there's no need. It's going to be exactly the same behavior as this SA. Because what's going to happen when you get it incorrect for the 3rd time in a row is the door is going to lock. It's going to close, the light's going to be off, and the alarm's going to start blaring. So it's exactly the same as the state. And that, I believe, is, yeah, that's it for the basic one. There was one where you had to come up with a way to make it so that it only alarms for 60 seconds and then it turns off after 60 seconds if no swipes have occurred. That's like an extra additional thing you could do to modify this. It's a very simple modification,
Just one more state.
but it might not seem simple until you do it. And it involves another concept you maybe have not seen yet. But for the most part, this is it. That's the state transition diagram. Okay. Any questions for me?
It's not so bad once we talk it through.
It's not meant to kill you.
When you first introduced like the FSM, when you said the door would lock when it was open, I thought like the locks would just pop out rather than it's automatic.
Ah, I see. Yeah.
Yeah. Wait, sorry. And so you said that there was like another concept that we may not have learned yet.
Well, it's not about a concept you haven't learned. It's just like an approach that you might not think about. So you know how in this one we said, okay, if we get something wrong, we're going to go to a state, and we're using the states to basically count how many times we did something wrong. Well, in the example that I'm describing to you, our system runs off of a 100 millisecond clock, which is a 10 hertz clock. And the problem was asking us to make it so that it waited 60 seconds. So in other words, that's 600 clock cycles. So we'd have to count 600 times, which is like 600 states.
Yeah.
Or 600 twice, because you have two paths, so 1,200 states. It's like, I mean, I guess I can draw that out, but that's a lot of states. Why would I do that? So instead of counting using the number of states, what you can do is have just a single state. And you can have a counter running off to the side. And basically what happens is, if you're in this state, we'll do the alarm state. And we say, okay, every single clock cycle that we remain in this state, that we're still in the state, we need to increment our count. So you have your FSM here. And inside of your FSM is your state register, and your state register tells you what your current state is. So I'm going to take that wire, the current state, and I'm going to run it over to another circuit. I'm going to say, okay, I'm going to put this in a circuit. And that circuit is going to be a counter.
I just learned counters today.
Yep. Yes, you did. Okay. S. So this little block right here just basically converts the current state, whatever the binary encoding of it is, into a 1 or a 0. 1 if it's the alarm state, 0 otherwise. So it just depends on how you do your encodings. That'll change this, but you can drop a truth table for it. So that's what this little block in here is. So every time a clock edge hits, and actually this shouldn't be there, this should be here. Every time a clock edge hits, this register is going to read in the next value, but the next value is going to be 1 only, or it's going to be whatever it was, plus 1, only if we're in that alarm state. And so what you can do then is you can take this value. This is a multi-bit value. Specifically, it has to be 6 bits, because in order to encode the numbers, actually no, more than that, we want to be able to count 600 clock cycles. So we say, okay, 2 to the what is going to work? It'd be 2 to the 10. 2 to the 9 is 512. That doesn't work. So 2 to the 10 is 1,000 something, 1,024. So that'll be enough. So we need 10 bits here. And so we have a 10-bit signal. And so we take this and we ask, is it at 600 yet? So we take this signal and we say, is it equal to 600? This bit on this wire on the other end is going to say it's a 1-bit signal, and if it's on, then that means we're at 100. If it's off, then that means we're not at 600. I said 100, I meant 600. So in other words, if this bit is on, we can leave the alarm state. Because if this bit is on, then we reached a count of 600, and so that means we should leave the alarm state. And so all that would change is that in this alarm state, if you receive the correct input, yeah, it'll go back. But if you don't receive the correct input, and you don't leave the alarm state according to this count, so if not leave alarm, then you stay here. If this signal is on, I don't know why I put that bar there. If this signal is on, then you're going to go straight back to the reset. That's the extra functionality that you haven't necessarily seen in class yet.
So you just draw this little piece completely separate with your leave alarm wire, and
It just depends how you want to do it. Like, It just depends how you want to think about it. You can think of this as being part of the FSM because it is. It reads the current state and affects the next state, so it's kind of like an internal thing. But for me, it's easier to understand it kind of like as an external circuit that reads from the FSM and feeds information back to the FSM, almost like a control unit for it. It's almost like a controller for the FSM. Funnily enough, though, FSMs themselves are control units, so this is like a control unit for the control unit. So if you don't like thinking of it that way, yeah, it's an internal circuit in the FSM, you'd have it in there. Yeah, that's about it.
That was great. Did they just have you do the state transition diagram, or were they then?
We had to do
like-
this, and then we had to code it up in Verilog, or
Oh,
System
okay.
Verilog, and then run it through Test Bench to show that it worked.
You had to create your test bench on the fly.
No, they made it. They made the test bench. They basically just fed us inputs from the keycard reader, and it was. There was one other minor nuance that I didn't add in because it's kind of not something you'd put on this diagram, but they also wanted you to account for if the input was undefined, i.e. not a nice digital value, zeros or ones. And there's a way to do that in System Verilog where you say equal x's for an undefined value. I didn't want to bring that up because it's not too relevant to this stuff.
Were you allowed notes when you had this?
Actually, yeah, they said if we wanted to, we could look stuff up.
Really? Okay, that, like,
Though, I'm going to be honest, I don't know how much that helped.
Yeah.
Except for like syntax stuff. maybe.
syntax, yeah, I'm
Just
thinking
syntax
like,
stuff.
if you don't, for System Verilog, if you ever have to look some. So is your internship, you're going to be using System Verilog?
Mm. They do VHDL mostly, so I'll probably have to learn VHDL. I don't know what I'm doing because they said they'd let me know what project they assigned me to on the 16th. Because I think they're going to be doing different projects for different interns depending on their experience.
Very cool.
So we'll see. I don't know.
So cool.
Any other comments, questions, concerns, grievances?
No, but I will say commenting that, like, I do like the real life examples. Those are really helpful.
In Dr. Harris's book, she has questions that were also asked in interviews, and some of them are FSMs. You can take a
Like
look.
a garage door opener?
That might have been one. I don't know. Probably.
Or a pattern detector?
I'm sure that someone's been asked in an interview to do something like that. So the moral of the story: you know how to do this. It might not feel like it when you first hear the problem because it's super complex, and that's your job. You have to break down a hard problem into smaller, simpler things to understand. You need to make something to control a door. Make an FSM. How do you make an FSM? What functionality do I need to make? What are my outputs? What are my inputs? Oh, that's your black box. That's your first step. Second step, start figuring out how I want this to behave depending on my inputs, et cetera, et cetera. So you do know how to do this stuff. It just feels hard, which it is. It is hard, but it's fun too. All right. Take one last picture of this in your mind's eye, and it's going to be gone. All right. It's okay though. You can just look at it in the video if you want to see it. Okay. All right. So that is the end of office hours. I will be here tomorrow at same time as usual. Let me think. You guys, your homework was due today, right?
Yeah.
What is it? Homework 9? 10? 9?
So I'm sure, is there one due on Wednesday maybe?
Probably. She hasn't assigned it yet?
I haven't seen it. Big Noodle, have you seen the homework assigned? I don't think it's in there.
I'm taking a look at it now, and it just says homework 9.
Yeah,
Oh, okay.
It's not on
Well,
there.
hopefully she sends it out to you guys soon. If she doesn't, then that probably means you won't have something due on Wednesday. If she doesn't send it by tonight, no promises though.
Yeah, there's nothing here. 110 yet.
Should I email her and tell her to assign you guys homework?
I definitely need to start working on it tomorrow. If it's not up there,
We'll see. Maybe. All right. I'm going to go ahead and end the recording. Thank you guys for coming office hours.
Thank you so much.
You're very
Thank you very much.
welcome.